Good morning, welcome back to 5-Minute Code. This is day 23, Amphipod. A group of amphipods notice your fancy submarine and flag you down. With such an impressive shell, one amphipod says, surely you can help us with a question that has stumped our best scientists. They go on to explain that a group of timid, stubborn amphipods live in a nearby burrow. 4 types of amphipods live there: amber, bronze, copper and desert. They live in a burrow that consists of a hallway and 4 side rooms. The side rooms are initially full of amphipods and the hallway is initially empty. They give you a diagram of the situation, your puzzle input, including locations of each amphipod, A, B, C or D, each of which is occupying an otherwise open space, walls and open space, for example. The amphipods would like a method to organise every amphipod into side rooms so that each side room contains one type of amphipod and the types are sorted A to D, going left to right, like this. Amphipods can move up, down, left or right so long as they are moving into an unoccupied open space. Each type of amphipod requires a different amount of energy to move one step. Amber amphipods require 1 energy per step, bronze amphipods require 10 energy, copper 100 and desert 1000. The amphipods would like you to find a way to organise the amphipods that requires the least total energy. However, because they are timid and stubborn, the amphipods have some extra rules. Amphipods will never stop on the space immediately outside any room. They can move into that space so long as they immediately continue moving. Specifically, this refers to the 4 open spaces in the hallway that are directly above an amphipod's starting position. Amphipods will never move from the hallway into a room unless that room is their destination room and that room contains no amphipods which do not also have that room as their own destination. If an amphipod's starting room is not its destination room, it can stay in that room until it leaves the room. For example, an amber amphipod will not move from the hallway into the right 3 rooms and will only move into the leftmost room if that room is empty or if it only contains other amphers. Once an amphipod stops moving in the hallway, it will stay in that spot until it can move into a room. Once an amphipod stops moving in the hallway, it will stay in that spot until it can move into a room. That is, once any amphipod starts moving, any other amphipods currently in the hallway are locked in place and will not move again until they can move fully into a room. So are we saying they have 2 movement stages? They have one stage where they move and then move out of the room and then stop, and then another stage where they move into a room and then stop, and that's all. In the above example, the amphipods can be organised using a minimum of 12,521 energy. One way to do this is shown below. Starting configuration. 1 bronze amphipod moves into the hallway, taking 4 steps and using 40 energy. The only copper amphipod not in its side room moves there, taking 4 steps and using 400 energy. A desert amphipod moves out of the way, taking 3 steps and using 3000 energy, and then the bronze amphipod takes its place. Leftmost bronze amphipod moves to its room in a single step. Both amphipods in the rightmost room move into the hallway, using 2003 energy in total. Both desert amphipods move into the rightmost room. Finally, the last amber amphipod moves into its room. Okay. This almost feels like you might be able to solve it by hand. So I'm saying the rightmost D goes I'm saying this bloke, the D, goes up and left. And the B goes up, up, right. And then this D, and then the D here goes down, down right, down, down. And then that D is parked. And then this D goes up all the way across down here, and then he's parked. This C goes up to there. Both of the A's go into their hole. Both of the B's go into their hole. Both of the C's go into their hole. And then that's solved. So I'm going to write this down in a funny form. So we have 2 steps from D. 1, 2, 3 steps from B. And then this D goes into its hole, which is 3 steps from D. Then the other D goes into its hole, which is 1, 2, 3, 4, 5, 6, 7, 8 steps from D. And then the C moves out of the way. Okay, and now we have either C moves out of the way and A's park, or A's move out of the way. It's going to be better for A's to move out of the way because C's are 100 times as expensive to move. So what have we got? We've got a B parked at the top right and both D's parked. So the A's now need to move out of the way. So we go 1, 2, 3, 4, 5A, 5A. And now the C's can move into position. So the rightmost C goes Well, the rightmost C takes 2 steps out of the way to let the B out. And now the 2 B's can park. 1, 2, 3, 4, 5, 6. And this one was at 1, 2, 3, 4, 5, 6. Now the 2 C's can park. So one goes 1, 2, 3, and the other one goes 1, 2, 3, 4, 5, 6, 7. And now the 2 A's can park, which is 1, 2, 3, and 1, 2, 3. And I think that's the solution. So if we add these up, we've got 2,000, we've got 300. No, hang on. These cost 10. That adds up to 14,266, unless I'm mistaken. Too high. Okay, there's a shorter route than that. Let's try and imagine what a shorter route would look like. Well, we can label some of these as definitely required. Well, this is on shortest path. There's no way for B to get to its destination shorter than 30 steps. This 3D is on shortest path. 8Ds. Is that actually 8 steps? So he goes 1, 2, whoops. 1, 2, 3, 4, 5, 6, 7, 8. Another one went 1, 2, 3. Yeah, so this is shortest path. Now the A is moving out of the way. What if the A is moving out of the way? Go 1, 2, 3, 4, 5. And the other one goes 1, 2, 3, 4, 5. And that's to allow the C to come out. But what if he went 1, 2, 3, 4? Then at the end, instead of 1, 2, 3, he'd have 1, 2, 3, 4, 5, 6. So that would be longer in total. So let's plot what we're like after here. So what we've done is we've parked both the D's. We've moved a B, 1, 2, 3. Maybe that's the mistake, 1, 2, 3. And then we've parked both the D's. And now we're in that position. And this has cost so far 13,030. And from here, what's the shortest path? Well, we need to get the C's into their hole. This C is going to have to come out to let the B get into its hole. We don't have a D there, that's an empty space. So if this C comes out, is it going to be quicker to write a program to do this? I think this A goes 1, 2, 3, 4, 5. And this A goes 1, 2, 3, 4, 5. And then we park the first B, 1, 2, 3, 4, 5, 6, 7. So this B would go 1, 2, 3, 4, 5, 6, 7. And this B would go 1, 2, 3, 4, 5. So we've moved the two A's. We've parked the first B. We need to move the C out, which is 2C for 200. And then we can park the second B, which costs 1, 2, 3, 4, 5. Then we've got the two B's parked, and we've got a C here. So we can park that C, which is 3C. Then we park the other C, which is 1, 2, 3, 4, 5, 6, 7, which is 7C. And we park the two A's, which is 1, 2, 3, and 1, 2, 3. Well, that's a further path than it was before, isn't it? Or is that equal? I think that's equal. Yeah, that's still the same length. How frustrating. Maybe I will have to write a program for this. Well, this C moving out of the way has to happen to let the B out. The 3 and the 7, given that the C has had to move out, this is the shortest way for it to get to the... These are the shortest way to park the C's. Oh, I know what to do. No, this isn't on shortest path. What we need to do is park the A's first. So the D steps out 2, and then the B just goes on the shortest path to its destination, which is 1, 2, 3, 4, 5, 6, 7, 8. And then where we've got 1, 2, 3, 4, 5, 6, 7, we just don't have that anymore. And then is that what we end up with? The D's gone 2 steps. The B's gone 1, 2, 3, 4, 5, 6, 7, 8 steps. The D's then gone 1, 2, 3 steps and parked. The other D's gone 1, 2, 3, 4, 5, 6, 7, 8 steps and parked. The A's have moved out of the way. Now what's this? 2090, I think. Now when we're here, the C moves 2 steps to let the B out. The B moves 1, 2, 3, 4, 5 steps and parks. C moves down into the slot it just came out of and parks. The other C goes 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7 and parks. And then the two A's park. And now what's this? That's 1256. So what do we get in total? 1, 4, 3, 4, 6. Yeah, that was fun. Yeah, so now probably we write the program, right? What did it say? Part 2. As you prepare to give the amphipods your solution, you notice that the diagram they handed you was actually folded up. As you unfold it, you discover an extra part of the diagram. Between the first and second lines of text that contain amphipod starting positions, insert the following lines. Okay, between the first and second, so there's a DCBA and a DBAC. The amphipods still want to be organised as before. What is the least energy required to organise the amphipods? Well, I wonder if we could actually solve this one by hand. I don't think so, because it's actually not obvious to me that a solution exists. Because if we just look at how we would want to fill up the column with the D's, then we need to be able to park the A, the C and the B somewhere. So, okay, we could move the D up and to the right, and the A up and to the right, and then the C and B up and all the way to the left. And then the 3 Ds from the left column can come down to the right column. And then we've got AD stuck at the right. What if we move the D to the right, the A all the way to the left, and the C to the right and the B all the way to the left, and then these 3 Ds come in, and then this C on the left only needs to go up and to the right, and then the B that's at the left can move across to the right, and the A can come down into its pocket, and then the other A can come into its pocket. The C can move across to the right, the B can move probably to the left, and then the other A can go in its pocket, and then the B can come in its pocket. This C moves out the way, the B goes in its pocket, the A goes in its pocket, the B goes in its pocket. Maybe we can solve this by hand. I'm going to give it a go. It would be handy to have them as like something that I could just move around and it would track the cost for me. No, let's write a program to do it. But what's the best way to represent this? Well, we have 4 pods of 4 types. The cost of each type is 110, 100,000. And their positions and happily that's already a comment. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Is that 11? 3, 4, 5, 6, 7, 8, 9. 11 spots in the corridor. How are we going to represent the graph? We need to be able to get the list of neighbouring locations for any location. And we need to know if you're allowed to stop on a spot, and if a spot is a pocket, who it's a pocket for. So we'll call the spots spaces are numbered 0 to, well, there's 11 and then there's 16 more. The ones you can stop on are, well, we'll have not stoppable ones, are the ones outside the doors, which are 2, 4, 6 and 8. How are we going to get the list of neighbours? This feels like some stupid way to build the graph. So we've got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 there. So 11 is connected to 3. Four times J plus I. What do you reckon? Maybe I'll just read the grid into memory and operate on the grid, because this feels really stupid. We need to use the heap to make a queue. And what is the state going to look like? It's going to have a position for each one of these things. Oh man. This isn't really that conceptually complicated. The problem is doing it without doing loads of memory copying. What we'll do is go over the grid. Well, how would I do this in Perl? I'd just copy the grid and stick that in my queue. Let's process this grid into the graph that we were going to have. Okay, what we'll do is we want to mark the dots with the space ID, with like a node ID in our graph. So we'll overwrite them. But we also need to know what the starting spaces are for each. So either 0 or a character. Now otherwise we'll write -1. Oh, so we don't need that, that's just exactly the same, isn't it? want to know for a given ID what it's a pocket for. Which in this case is nothing. And in this case is X is 3579, maps to A, B, C, D. Okay, that's our grid then. And a state in the graph is malloc n spaces plus 1. So the first n spaces tell us what's on each space, and the final one tells us what the cost is. Now we just want Dijkstra's algorithm. And we want to return now. We want to go over each piece that can move. So if there's a piece on this square, then we might want to try to move it. Which squares can we move it to? Oh, that's actually really annoying. Maybe we'll transform them to lowercase. So they start out as uppercase characters. Uppercase characters have to move out of a pocket. They turn into lowercase characters once they've moved once. Lowercase characters have to move into a pocket. So if it's a lowercase character in a pocket, we do nothing because he's home. So we want to depth first search through state to find all the places this person can move to and push all those possible states onto the queue. I wonder if the cost is going to overflow 16 bits. What we want is every pocket to be occupied with its correct type of thing. So for each space that's a pocket, if you uppercase the thing that's in that pocket and that doesn't match what it should be, then it's not solved. So move So we'll look at every neighbouring point for this point, and if that point is not occupied, then we can move to it. And if we don't need a pocket, then we can terminate our move here. Oh, we also need to know if we've already visited it. Ugh. So M is the point we're moving to. If we haven't visited it and it's empty, then if we don't need a pocket, then we'll have a new state. At the end of here, through the state. So the new state is number of spaces, momentum copy. Oh, so if we don't need a pocket, or it is a pocket, but it matches what we're looking for, then we can move into it. Unless something below that point in the pocket contains the wrong type of thing. Maybe we'll just ignore that. So we copy new state from state, but new state n is 0, new state m equals a state n, and we'll push the new state onto the queue, and we'll recurse. And I think we can mark it as visited here. Because there's only one, from any point in this little corridor thing, there's only one route to any other point. So we don't need to worry that the depth first search will deeply reach a point and then there's actually a shorter path to it. But actually, we need to update the cost, don't we? So new state n spaces is equal to state n spaces plus the cost of one move for this type of thing, which is cost of 2 upper state n minus a. There, maybe that'll work. I wonder how long it'll take. It'll probably run out of memory. There's no 2 upper. I think we'll try and get it to do part 1 first. Yeah, okay. Is it doing the right thing and running out of memory? Or is it doing the wrong thing and running out of memory? I didn't put I++ on that one. Don't any others where I forgot I++ are there. I just remembered that we need to make them lowercase. So, having done the DFS, we just say new state m equals to lower. So that we know we need to move it into a pocket. Well, that looks about right. Yeah, it runs out of memory on part 1. Well, it's not obvious that it's working correctly. But I think it's likely to run out of memory on part 2 anyway, and I expect part 2 needs a big int. And I'm actually pretty much out of time. But that's the general form of the solution I would like to create, which is Dijkstra's algorithm over a graph of possible states, where the transition from one state to another is a movement of one amphipod either out of a pocket into a pocket, out of a pocket into a corridor, or from a corridor into that amphipod's pocket. Yeah, I can't see a better way to write the solution, but I can't do it in the time I have available. Anyway, thanks for watching. Goodbye.